Okay, so I want to talk about change of variables in multiple integrals. So we've already seen examples of this with polar, cylindrical, and spherical coordinates, and at the time I sort of drew pictures for you to indicate why you should believe the fudge factors that are showing up. So what I'm going to do today is state the general theorem, and I'm going to do a bunch of examples today and Wednesday, and by the end of the week I will make some effort to give you an idea why you should believe the theorem. The actual proof goes on for something like 5 pages in the book. There is a mistake in it, so if you're actually trying to read it, you should look at the errata on my webpage and make sure you correct what's incorrect. It's been done. So why do we expect determinants to be involved if we're thinking about integrals?
Because determinants are area of hyperparallelism.
So recall that we talked about in chapter 1, we said that if you took 2 vectors in the plane, then the determinant of the 2 by 2 matrix you get putting the vectors in gives you what? Geometric? Close. Sine area. So we had this picture that if you had 2 vectors in the plane, then the determinant gives you the signed area, where sine means what? The sign.
It goes left, clockwise or counterclockwise.
Right. So it keeps track of whether you're making a right-handed system there or a left-handed system in the way the physicists think about it. So if you rotate counterclockwise to get from B to W, you get a positive area. If you rotate clockwise, you get a negative area when you do the determinant. And you will recall that when we did this discussion, we talked about why the properties of determinant were really the same properties of signed area. So in particular, if you switch the 2 vectors, that switches the sign. Next property was if you multiply a vector by a scalar, then the determinant multiplies by the scalar. Well, same thing's true for area, right? If I rescale one of the sides of the parallelogram, then I'm rescaling the signed area by that same quantity. Clearly, if I took the standard basis vectors, I get determinant 1, but I also have area, signed area 1. And then the interesting one was the one when you did sums of vectors. If you replaced B by a sum of 2 vectors, remember we had a picture proof that you were actually seeing areas adding up. But you can also see it, that property is equivalent to saying if we shear and add a multiple of V to W, then we're not changing the signed area. That's equivalent to property 3. And so that's basically the principle that you know by the name of Cavalieri's principle from high school. Do you remember that from geometry? Everyone's saying no.
Never heard of it.
That's the first time I've ever heard of it.
Yeah.
Funny.
Isn't Google wonderful? You can all go learn about it.
Yeah.
So that's basically the shear principle we talked
So
about.
Cavalieri's principle, and this goes back really to Archimedes, says if you have 2 objects of the same height, and at each height they have corresponding cross-sectional areas the same, then they have the same volumes.
My class went into this Clark Central, and they were learning that
Oh, really?
just last week.
So this is a special case of that, where you're saying this cross-section is just the original one of the original parallelogram slid over, so you haven't changed the area. You haven't changed the length of the cross-section. When you just shear, you're not changing that cross-section area or length in this dimension. So I'm going to say that basically these same discussions apply in n dimensions when you're doing volume of a parallelepiped. That you see that the properties of determinant are exactly the properties that sign volume should have. And more generally, so the same holds for vectors v1 to vn in Rn, that the determinant should be the sign volume and in fact, and this is actually proved in the book, more generally, for any region in omega in Rn, and any linear map T mapping Rn to Rn, if you take the sign, the absolute value of the volume of the image of omega, it's going to be the determinant of T, absolute value, times the volume of omega. So the idea
Do you remember
behind
how to
this,
use absolute value with volume? Can you have negative volume?
oh, never mind. Thank you. I was thinking about writing signed and then decided I wanted to make sense of what that meant, so yeah. Thanks. So if you had a region, so here's Rn, and suppose you had a region in Rn, how would you even define volume of the region? Do you remember how we do this? You take the function that's 1 on the region and 0 everywhere else, if you like, and integrate it. So what you're really imagining doing is putting omega inside some rectangle and partitioning the rectangle, right? And basically, you're imagining keeping track of which rectangles stay completely outside of omega and which rectangles stay completely inside omega. And if omega is a region, that means you can make a partition where the sizes are small enough and you get as close as you want with upper sum minus lower sum for doing that process. So when you apply your linear map to omega, it changes its shape. And in fact, each one of these little rectangles in there turns into not a rectangle. What does it turn into? It turns into some sort of parallelepiped in higher dimensions. And so you're now, instead of covering up omega with rectangles, you're covering up T of omega with parallelepipeds now. But the point is that what happens to the area or volume of this rectangle is exactly that it multiplies by the absolute value of the determinant of T. Because if you imagine taking standard basis vectors here that point in the direction of the sides of the rectangle, and you apply T to them, what you get is the columns being the images of those vectors. And I've already said that you should get the sign volume when you do the determinant of that matrix. So this formula actually can be proved more carefully, and if you look at the book, it's written out there. But this is meant to suggest to you that you should expect determinants to show up if you're trying to distort under some sort of mapping. You take a region and map it, then you expect absolute value determinant to show up when you want to relate the volumes. So, here's the statement of the theorem. And we're going to spend the rest of today and a good part of Wednesday doing examples. Theorem. Change of variables. So here's the setup. You've got a region in Rn, just like I was drawing here. And you're going to map said region. So you have omega. And suppose you have a mapping on a slightly larger open set. That is at least C1, or more differentiable. And suppose it's 1-to-1. So G is going to map U into some other set, and it's going to map my omega into some region G of omega, which I'm going to call S. And what I want to do is integrate some function over this region. So I have in my picture a function, a real value function, that's defined on region S. I guess I should be glad it was not something worse than that.
I don't know, you didn't do it, Ted.
I'm not that artistic. So suppose F mapping S to R is integrable. Then, integrating F over the region S, I can rewrite as integrating fog back over the region omega. So you want to instead write in terms of the variables back in omega. So you want to integrate fog, right? X over here. X in here is going to be G of a point U in omega. So I'm going to integrate fog of U, dV over the U variable. It does look like U substitution. And what has to come in here is the fudge factor. So what comes in here is the derivative of G, determinant, absolute value.
The determinant of the derivative matrix of G?
Yes. Okay. So this is the fudge factor.
It's G of U, correct?
It's the derivative of G at U. And I'm going to put a provided here that this function here is actually an integrable function. So I'm going to make that a hypothesis. But in fact, that's not a big thing to worry about if you know F is integrable and G is well behaved. But phi of U that dg of U
Why is it
integrable.
Why is it dg of U?
Well, because as Cameron said, I'm making a change of variable, so I don't want to use the same letter in both places. Just like when you write a substitution in an integral, you use different letters for the two integrals.
So is this referring to U up there?
Well, sort of.
If it's inside of omega?
But it's inside of omega. So I'm using U to represent my points here, and X, G of U here.
So all you U's are inside of omega?
All my U's in that integral are inside of
Right,
omega. But I needed to be official, to say what it means to be C1 on a region I needed on a slightly larger open set. In practice, we're not going to worry about these technicalities. But so the cool thing you want to think about is, given a problem, either the function f or the region S suggests some sort of change of variables, where I write x as g of u and make an integral in terms of u that is actually easier to do. So for example, then this is consistent with what we've been doing with polar coordinates. For polar coordinates, we have g of r theta, so those are my u equals x, y, and if I compute the derivative matrix of g, I think we actually did this the other day, right? You get cosine theta minus r sine theta, r cosine theta, and the determinant is r. So there's the fudge factor. And that's exactly what we were doing when we rewrote our integral over some region in the xy plane as an integral over the region in the r theta plane. Any questions on what we're stating here? So let's do a simple example before we start doing fun stuff. Suppose you wanted to integrate over a filled-in ellipse. This actually showed up in one of your web work problems if you did the problem wrong. There was a problem a week ago where, I think it was the last problem on the assignment, where I said, hint, you don't want to integrate it over a region in the xy plane, because if you had done the xy integral on the outside, you would have had to integrate over an ellipse.
I think those hints is challenges.
Why is that not surprising? All right, so now let's discuss. How would you actually, if you had to take a region S that was, say, the region x squared over 4 plus y squared less than or equal to 1. Suppose you were supposed to do some integral over the inside of an ellipse. Can you think of a clever way to do that, rather than trying to use Cartesian coordinates?
Linear transform.
Forget Wolf math. It won't be there for your test. So, linear transformation from a disk, right. So if you take, there's an obvious linear map that takes the unit disk to this ellipse that is slightly off kilter the way I drew it. Okay, what's the linear map?
It's just,
Linear map.
just figure out how it changes the standard basis vectors and then you make the,
Yeah, it looks like it.
2x and y.
I need using V's. Right, here's my UV space, here's my XY space.
2u and v.
And notice that if you plug this in for x and this in for y, that cancels out the 4. And you have exactly that u squared plus v squared is less than or equal to 1. So that means the unit disk in UV space is mapping under this linear map to this filled-in ellipse. Now, if you actually wanted to integrate in practice, how would you integrate? Okay, so what do we see? We see that if you apply the change of variables theorem, integrating over the ellipse would turn into an integral over the unit disk here of f of 2uv, and then what's the fudge factor? Which is what? What is this matrix that gives the linear map?
2, 2, 0, 0, 1.
What's the absolute value of the determinant?
1 or 2, sorry.
2. So you would get 2 would be your fudge factor, and then you would have dA in the UV plane here. Now in practice, how would you do an integral over a disk most of the time?
So then, polar.
polar, right? So in practice, and this is what Yimen was starting to say before I cut her off, in practice what you might rather do is do a stretched polar coordinates. In other words, compose this linear map with polar coordinates parameterizing the disk and use that transformation instead to parameterize S. Does that make sense? So we could now compose with polar coordinates and so if you wanted to be slick about it, you could look at T composed with G, right? Polar, then stretch, and that would parameterize from polar to our original region S.
So then your fudge factor would be 2R?
That's exactly right. Remember the product rule for determinants. So if you took the derivative of a linear map composed with G by the chain rule, that's, what's the derivative of a linear map? It's self, right? Linear maps are their own best approximation. So this is the composition of the linear map with dg, and the determinant of this by the product rule is the product. So exactly as Lama said, you get the 2 from this and the r from this. Of course, you could just write it down and do it brute force. But. Okay. So, cool fact. If you take the ellipse with semi-major axis A and semi-minor axis B, what's its area?
It's pi a b.
Right? Now you have the fudge factors AB. The area of the unit disk is pi, so when you do the area computation here, you just get the fudge factor times the area of the disk. Same thing works in n dimensions. If you take an n-dimensional ellipsoid that you take by taking a unit ball and stretching it different amounts in different directions, you get the product of those semi-minor, major, medium axes. Mm-hmm.
So can we, before we just learned recently, can we just keep messing with shapes and stuff until we get it where it's a really simple looking figure?
That's your
Or
goal.
like weird fudge factor?
I mean, that may or may not, you may end up, having done that, you may have made everything else so complicated it didn't get you anywhere, but that is sort of the goal. So let's now do a bunch of examples. So I'm going to warm up here with some pretty obvious ones, and then by Wednesday we'll be doing some less obvious ones. So let's say we have the following region. So I'm going to draw the XY region here, and then we're going to keep our U space back here to map. So let's see. So I have the line y equals 2x. The line y equals 2x plus 1. The line x plus y equals 0. And the line x plus y equals 3. And this is my region S. So it is a parallelogram. And you could actually figure out what vectors make that, the sides of that parallelogram if you wanted to. And suppose I wanted to evaluate the following integral, which I now have to change because I changed the problem slightly. This is going to be very convenient. 2x minus y over x plus y plus 4. And you want to integrate this over S. So the person who made up the problem was being very obliging because the functions that are appearing here are very nicely related to what's defining the sides of the parallelogram. It doesn't have to be that nice, but let's warm up with this problem first.
Let's go to UV space.
let's go to UV space. So you want to say to yourself,
So,
what mapping do I want from UV space to XY space that'll map a nice simple region to my parallelogram S?
make it square.
So wouldn't it be nice to make it be at least some sort of rectangle?
Just rotate it.
Whoa, I don't want to rotate.
You don't?
These are not right angles.
Oh, okay.
But I mean, if you were just doing this the way you did baby calculus, you wouldn't think about the mapping yet here. You would think about what can I substitute to make the integral look simpler. So what would you be inclined to say to yourself?
So,
Let u equal and let v equal, and what might you use?
X plus y, 2x minus y.
So 2x minus y would make that simpler, and x plus y would make these things simpler. So Will is not worrying about the 4 at the moment, although we could put x plus y plus 4, couldn't we? Who wants to do what? X plus y, you want to do what Will said, or do you want to put the 4 in there?
I feel like you want to put the 4 in there.
I don't care.
Let's put the 4 in there. See what we're going
So this becomes u over v. That's not bad. But now notice, by making this substitution, am I giving you this mapping? What am I, so other than Will, what am I actually doing here?
You're giving us,
Are you
it's going to
giving
be a
us the
square,
inverse?
right?
You're ahead of me, but am I giving the mapping from uv to xy?
no, you're going the other
I'm
way.
going the other way. When I write this down, I'm actually giving you G inverse. Right? I'm saying what's u and v in terms of x and y. So that's going this way. Well, okay, just so long as you're aware of it. Can you figure out a region back here that would get mapped to S by the inverse of this transformation? Well, look at the equations. What are the sides of the parallelogram? What's this side?
U. Of 1. Of 0.
U equals 0, right? U equals 0 maps to y equals 2x. What about y equals 2x plus 1? So u equals -1. So you might prefer, maybe you would rather have done y minus 2x if negatives flip you out. Right? So these lines are mapping to these lines. What about x plus y equals 0?
V equals -4. Or no, 4.
4, right? If x plus y is 0, v is 4. And what about x plus y equals 3? X plus y equals 3.
That means
V equals 7.
V equals 7, right? So my scale isn't quite right here, but here's the omega. It's a nice rectangle that's mapping to S. Under the mapping that I haven't written down yet. So if someone made you figure out G, what would you do? How do we figure out G?
Just solve for x in terms of u and v, and y in terms of v.
Sounds like solving systems of linear equations, doesn't it? So, what do we got? So we've got u equals 2x minus y, v equals x plus y plus 4. So how can I convert this to a system of linear equations?
Y equals 2x minus u.
No, I'd rather use stuff we've learned in this course rather than going back to 9th grade.
Do you want to set up?
Some matrix times xy equals what? It's not going to be UV. If this is linear, I can't have the +4 in it. 2x minus y equals u. Agreed? Now what's the next line?
1, negative.
1, 1, v minus
Or should you do like 1, 1, y over 4?
V minus 4.
V minus 4, right? Now you have a system of homogeneous equations, well, not homogeneous, but a system of linear equations, and you actually can solve for g of uv is what? How do you give x and y in terms of u and v?
I think the inverse matrix and multiply v minus 4.
Okay, so if I take the inverse of the matrix, which we can all do, what is the inverse?
2 plus 1/3 times 1, 1, negative 1, 2.
So there's the mapping, right? There's G.
So then take the derivative of that.
Okay?
And give this a fudge factor.
Mhm.
So we pull out 1/3 and the matrix. That's all in here.
So in particular, if you want to write it out carefully and without matrices, I suppose, what would you have? You'd have 1/3 factoring out, and what's x? U plus or minus 4, and what's y?
2v minus 8u minus 8.
Minus u.
Yeah.
Okay, so what do we get when we write down the change of variables theorem? So the original function integrated over s, according to the change of variables theorem, I now have an integral over this square omega, sorry, rectangle omega. What is f of g of uv? Don't overthink this.
Should it just be?
Now, what happens to this function when you put in x and y in terms of u and v?
Comes u over v.
We made it up so that it would be u over v, right? The whole point of this transformation was to make this be u and this be v. And if you really want to take the 5 minutes to check, plug 2 of these minus this with the thirds over that, and it should all work out if we haven't made a mistake. Now what happens to the rest of the right-hand side? There's fog of uv. What's the absolute value of the determinant of the derivative? So what is the derivative matrix for this transformation, for this function?
V minus 3.
1,
Derivative.
1, 1, negative 1, 2.
These guys don't matter, right?
1/3 times 1/3 times that.
Duh. Again, derivative of a linear map is itself. So you're getting this matrix and then we integrate dA in the UV plane. So what is the determinant of that matrix? Be careful.
3.
Jonathan won't make this mistake again.
3.
No.
Oh,
2 over 3.
1.
no, 1, okay, 1/3.
You guys all fail. Epic fail.
2 over 3.
No, it's 1/3, right?
3/3. Keep going.
Well, no, then, is it
It's 1.
It's 1/3.
It's not 1.
3?
It's 1/3.
It's 1 day.
It is. It's 1/3.
1/3 should be 1/9.
No, it's 1/3.
Look, guys, determinant of a constant times a matrix. You just got homework back.
You raise it to the length.
So it's 1/3 squared times the determinant of that, which is 3. So it's 1/3. How did you know that immediately? What's the determinant of A inverse?
It's 1 over the.
1 over the determinant of A. So if A is this matrix and the determinant is 3, 1 over 3 had better be the determinant of the inverse. All right, set up the iterated integral. V goes from what to what? 4 to 7. Doesn't matter what order you're doing because the problem is over a rectangle and it really is simple. U goes from what to what? So what do you get? You get 1/3 times the integral of u over v du. So you get 1/2 u squared from -1 to 0. And then you integrate 1 over v. And you get log v from 4 to 7. So you get that answer. Now, does that bother you?
Yeah.
Why does it bother you?
Well, I feel like we could have just done this by shearing a little bit. And then you get,
Really?
yeah.
We would have had conserved the area, but we'd have, the function's not the same everywhere.
Yeah, the function gets distorted now if you're. But why are we upset or not upset about the answer being negative?
I don't care.
Well, but
I mean,
it is good to use common sense and try to catch a mistake.
Well, the function values can be negative because,
So in fact, if you look at this function, the x plus y plus 4 is positive everywhere in the region. But in the numerator, 2x minus y is what? It's negative. Except on this edge, it's always negative in the region. Right? Because y is bigger than 2x. So you're integrating a negative function, the answer should be negative. Okay. Any questions? Okay, so I'm going to slightly modify that question. Suppose that we're over a different region. Suppose that we're over the region. So keep the integrand the same. Change s, keep f the same. So suppose my s now were y equals 2x on this side, x plus y equals 0 on this side, but I'm bored with parallelograms. I'm just over them.
We don't have the other.
So I'm going to draw a vertical line and say it's x equals 2. And now this is my region S. And now I give you the same problem. What do we do now?
I mean, now it wouldn't be so bad just to do the integral.
Do you really want to do iterated integrals with that mess?
Well,
I mean, you could. You could. But having done all the work we've just done, why bother? What do I have to change in the analysis I've done?
Like the v's and the u's in the graph.
There could be a line.
My green picture has to change, right? But it doesn't change that badly, does it? So what's the green picture now?
U plus 3 minus 4 divided by 2.
Well, hang on, slow down. So the line u equals 0 is still there. The line v equals 0, whoops. It's not u equals 0, is it? What have I done? This is u equals 0.
Line V.
X plus y equals 0 is the line v equals
4.
Negative 4.
4. Yeah, V equals 4 is still there.
Okay. So I've got those two, and now comes the interesting one. So I'll even give it preferential color here. What does that line become?
U plus V minus 4.
U plus B minus 4.
Minus 3.
You're not giving me an equation. So you guys are doing the right thing. What's x?
2.
What else is x in terms of u and v?
1/3 U plus B minus 4.
So we have to look at 1/3 u plus v minus 4 equal to 2, right? That's the equation of what maps to the line x equals 2.
U plus V equals 10.
So it looks like, what did you say, Reese?
10.
U plus v equals 10. Does everybody agree?
Yeah.
So u plus v equals 10. That's a line that looks like this. So where is my region that maps to S? Looks that way, doesn't it? It's got to have this as one boundary part, this is one boundary part, and this is one boundary part. That leaves only that option. If you're going to have a bounded region. Right? I mean, you could try to rig something outside here or outside here or something, but that wouldn't be compact. And we ought to have a compact region mapping to a compact region here.
So now we just plug in the limits of the integrated intervals.
So we might want to think about whether we have a preference on order of integration at this point, but now we're just going to have the integral of f over s would be the integral of fog again. Fudge factor is the same. Fudge factor is still the same. But now, at this point, you have an iterated integral and you want to decide which order you want to use. So it doesn't look any different to me in terms of the region, whether I do du dv or dv du, but would I rather have one order over the other for what I'm integrating?
Probably want to integrate the U first.
Integrate v first?
U.
I'd say.
I mean, I don't think it really matters.
Yeah.
Okay.
Just do U first.
You want to do u first?
Yeah, do du dv.
All right.
You do it first, then D's next.
All right. V goes from what to what?
4 to 10.
And for fixed v, what does u do?
It's from 0 to 10 minus V.
Integral of du is 1/2 u squared. So I'd have 1/2 10 minus v squared, all divided by v. Integrate dv, and so you just expand it out and do it. Right. Okay. Any questions? So obviously, after the test is over, you'll have web work to do with the stuff. So just since we still have 5 minutes, I've put another problem on the board for you to ponder.
If we hadn't missed the day last week, what would we have done? Or would we have just done this on Friday?
Basically,
But this is on the test.
no. Okay. So here is a more complicated looking problem. bored with the way I've been doing colors, so I'm going to do a different coloring scheme here. xy equals 1, xy equals 3, y equals x, and y equals 2x squared. What does that look like?
It's like a sharp
Y equals 2x squared.
Parabola, and it's certainly going to cut through here earlier than at 1, 1. Because at 1 it's a 2, right? So it's going to do something like that.
I guess you want to integrate the.
And you can guess that this is my region S.
Yikes.
So, I'm not even putting a function on the board at this point, but we could, for example, want to integrate y squared or something. Now, going back to Daniel's point a few minutes ago, would you choose to do that in Cartesian coordinates?
Oh, that'd be terrible.
Because that, yeah, the curve.
I'm guessing you'd have to split this up into
Three.
3
Yeah, I
regions.
think
No,
three.
only 2, I think.
Oh, really?
These points don't line up, I don't
Yeah,
think.
they don't line up, so yeah, but maybe if you did it the other way,
It'd still be
that's
three.
still,
Still three.
Yeah, so you could try to do that. You could be stubborn. Or you could say,
Say.
would there be some change of variables to entertain that might make the region look less complicated? So again, it's more natural to start off thinking about u and v rather than the mapping from uv to xy. It's more natural to think about what would be a good substitution. I can guess an obvious u. xy, right? But now I don't know what to do for v.
Couldn't you call x?
I would prefer x squared, probably.
I'd say x.
Why x squared?
Because you want, I mean,
Because then you'd have to
Just
just square
x.
root 1, and then
yeah, but it would be easier to have x and then 2x squared.
I mean, wouldn't you like to make one of these two curves be simpler in the new coordinates?
I feel like dealing with the squared
Yeah, b squared.
No, I don't agree.
Yeah, I was just thinking
What,
that.
Why don't you do one
what
over y?
substitution would make this line very simple?
1 over y? What if-
1 over x.
I thought you said it right a minute ago.
x minus 1.
I thought that's what you said. Right, then that makes this easy.
uv is y squared.
And then what does y equals 2x squared become? It can't be that horrible.
Yes, you can.
Why don't we do x over y instead of y over x? That might work better.
You think?
Yeah, I think it will.
But if we do y over x, uv is y squared.
uv, if you do,
Do y over x, uv is y squared.
Yeah.
whereas if you do this way, uv is x squared.
And you want x squared.
Well, but I have a y still.
Yeah.
All right, so we'll start off on Wednesday playing around with these and seeing what we get.
So is the